Hello, welcome to Convergent Dialogues. This is Xavier Bonilla. On this episode, I'm very honored to have the wonderful György Buzsáki. György is the Biggs Professor of Neuroscience at the NYU School of Medicine. He is one of those brilliant people that has an MD in medicine, obviously, and he has a PhD in neuroscience. And he is originally from Hungary. I believe that's where he got his MD. And he has his PhD in neuroscience from Budapest. And then he's done a handful of postdocs here in the US. And he has been teaching at NYU for the past 12 years. He is well established in the areas of, well, all things neuroscience, but neurosyntax, such as how brain rhythms support cognitive functions. He's done a lot of work on hippocampal networks, so many things that involve memory. And of course, he's a member of the National Academy of Sciences. He's a fellow of the American Association for the Advancement of Science, many other affiliations. He is the author of a handful of books, including the more recent, The Brain from Inside Out, which is the book that we talk about in this conversation. We start by talking about in versus inside out framework for understanding the brain, causation as problematic for self-organizing systems, perception and action. We talk about Bayesian brain, predictive processing, Carl Friston's free energy principle. Talk about the reinforcement, reward, and salience in gain control theory. We talk about brain systems and neurosyntax, brainwave oscillators, space and time and how that works within the hippocampus working in tandem with the rest of the brain, and some of the future of this inside-out framework for understanding brain-behavior relations. I got to say, in the last half to quarter of the conversation, it gets a bit dense in the best ways. We started talking about space, time in the brain and how that works, and I was, definitely over my head on it, but it was fascinating to listen to. I think I mentioned this, that, this is tough stuff, but really, really important, really, really essential. He's just an absolute genius, and he's done some really, really great work within neuroscience. You can find this conversation, all the conversation, at Convergent Dialogues at Substack.com. I'm also on YouTube, so make sure you like, subscribe, follow, share, contribute. All of that is very appreciated. And I bring you György Buzsáki. I'm here with György Buzsáki. György, thanks so much for coming on the podcast. I'm greatly looking forward to speaking with you. You are the author of the fabulous book that we're going to talk about. It's one of your handful of books. The book is called The Brain from Inside Out. This is through Oxford. Of course, you've written Rhythms of the Brain and many others. So we'll get all into everything the brain. But before we do, why don't you tell listeners kind of who you are professionally, academically, where your main research areas happen to be, and anything you're currently researching or up to.
I'm a systems neuroscientist, which is an interesting new term. I work at New York University Medical School. Our focus is mechanisms of memory, mechanisms of cognition, especially how sleep affects these processes. Our centerpiece is the hippocampus, and we reach out from the hippocampus to various parts of the brain. And our main method is neurophysiology. Within that large framework, we do experiments in rodents and occasionally in collaboration with others in humans.
Did you always start with memory in the hippocampus, or is that just kind of where you landed? How did you kind of get into this work?
Actually, my interest lies in neuronal circuits. So I found the hippocampus through my mentor many years ago, and I used to be a radio ham. I was interested in radio transmission, coding, such as the Morse code, and the brain, and especially brain circuits, were at some level of superficial level were similar. So that attracted me to try to understand how circuits transform information and use storing information. So that's the truth nature of our work. We try to understand brain circuits. That's the primary goal. And we reach out from this to see what their functions might be. And the reason why I chose this maybe comfortable attitude is that when you take a word, and we will talk about this later, and you try to understand the mechanisms of these man-made words, you take the risk that you are searching something that doesn't exist. Whereas if I study the brain circuits and I understand them, then I will contribute to neuroscience because that's solid knowledge. And so this is the general attitude. We have a saying in the lab that it's impossible to find nothing in the brain. So if you are studying the level of synapses or vesicles, everything, and you can still look at the world in its beauty and its large complexity, it almost doesn't matter what you are studying. The matter is how you frame your experiments and how you interpret them.
It's very interesting. You have we'll talk about this, but many people will talk about the world in terms of, outside in. So we have stimuli in the world, and then we take it in through our senses, and then our brain makes some kind of processing of it. And you have a kind of different way of looking about that. So I guess the question I want to ask generally is that in the book, your main thesis is that the brain is a self-organized system with pre-existing connectivity and dynamics that's used to generate actions and predict consequences of those actions. Why do you feel that an inside-out, as opposed to an outside-in, strategy is more accurate of understanding how the brain works for humans?
Because it makes more sense to me than the other way around. And in order to put it in the right framework, let's go somewhere else. Let's think about math and geometry. And you say, well, it's wonderful because in math and geometry, we make up axioms, we make up a few rules. And with the help of these made up rules, we can understand the system that is generated from those rules. Now, do we have such rules in science, or do we have such axioms in science? And that's a big question. We like to brag about science as an axiom-free approach, because the reality is out there. All we have to do is to learn about reality. Now, coming to neuroscience, that's an interesting thing, how we are trying to deal with reality. And just to summarize the many years of what happened in this field, or in this very large area of thinking, is something like this, that neuroscientists, which we call ourselves neuroscientists, that we bought into a system that was created by philosophers and psychologists for understanding not the brain, but the sound and the mind, without ever asking how those terms, whose brain functions we are trying to understand, such as consciousness, and all these complicated things, were brought into our thinking in the first place. So when neuroscience came into being, it inherited its paradigm from this philosophy-driven framework, which portrays the brain, or more precisely the soul and the mind, as a tool to understand something about the true nature of the world. Early thinkers used introspection and gave names to mental operations such as memory, emotion, motivation, decision-making, or free will, and so on. And now, a millennia or maybe 2 millennia later, millennium or 2 millennia later, we search for neural mechanisms that might relate to their dreamed up ideas and classes. Now, this is the interesting paradox that I try to portray, because obviously, if an idea is dreamed up, then it's very difficult to know that it was an axiom or it's reflecting reality. So the philosophy behind all this was that, of course, we were given the soul as an interpreter to understand the beauty of the world. And the soul was given to us by a higher authority to learn about him or them.
Mm-hmm.
And that made sense for a long time because you put things in this framework, namely Christianity or other religions. And then British empiricism basically bought into this Christian philosophy-based ideas that we have our senses, and the senses are given to us, and through the senses we learn about the reality of the world.
Mm-hmm.
But all of this, if you want, is human-centric. Moreover, it's language-centric.
Mm-hmm.
So many of the things that we define in neuroscience are based on language.
Mm-hmm.
A fantastic example for me that we are struggling with all the time is memory, particularly episodic memory.
Mm-hmm.
We can talk about the episodic memory mechanism later, but in a nutshell, it has a definition. Basically, it's part of declarable memories. That is, those memories that we can declare to each other through words.
Mm-hmm.
Now, that's a dangerous definition for us, or for us like me, because I'm working with rodents.
Mm-hmm.
And they don't communicate with words. But I think many of us agree that their memory system is fundamentally the same as ours.
Mm.
So we have to find something else that is a good definition rather than this human language-based definition. Now, this is just picking on words,
Mm-hmm.
but there are fundamental consequences of this thinking. Namely, that once you buy into this framework or philosophy, if you wish, that the goal of the brain is learn about the objective reality of the world. Then you've asked the first question, whose brain? Is it my brain? That have a brain of a spider, a fish, or another creature? And do we learn through our individual brains the same kind of reality that exists out there?
Yeah.
So understanding this, that framework matters, it's almost like saying axioms do matter. Because I can take one framework and I can build my system and everybody is happy within that framework.
Mm.
But the moment you're asking the next question, then maybe another framework will give you a different answer.
Mm.
Now, even within the same framework, which is in our case that we discuss now is the outside-in framework,
Mm-hmm.
there have been crises. And the crisis is simple. Namely, okay, the brain is there to learn about the world, to absorb knowledge,
Mm-hmm.
to perceive the world
Mm-hmm.
in its reality. But what is the purpose of all this? Is this useful for the brain? It's totally and absolutely useless in my framework unless you can do something with it.
Mm.
In other words, unless you can utilize that information to your own benefit. And your own benefit translates to something useful only through action.
Mm.
Now, here are the sensors, here is perception, here is the relationship between the world, but we have to translate in all of these things into action.
Mm.
How do we do that? Well, between perception and action, there should be something.
Mm.
Because that's not direct. It would be just a reflex, right?
Mm-hmm.
So wedge between these two complicated things, the fundamental thing that a student always asks from you is that, okay, now I understand that a rose has colors, it has texture, it has a form, it has this and this. These are the attributes of the rose.
Mm.
And then all we have to do is fuse or combine the attributes of the rose into something.
Mm.
So there are two problems here. One is that the attributes of the rose are not in the rose. They are in here.
Mm-hmm. Mm-hmm.
Second one is that who is doing the synthesis?
Mm.
So how do you bind all of these things into a rose?
Mm.
So then you go deeper and deeper and deeper in the brain, and then on the way you get lost. Now you have to say, I have to do something with the rows. That will be the action part. And how far I have to go back from the spinal cord from the brainstem and motor cortex and beyond the motor cortex and supplementary motor cortex and even all the way to the hippocampus. Then you say, okay, now this is where the action starts. So the funny thing is that in the middle in between the input and the output, there is this interesting territory that fascinates most of us. You can call it cognition, or you can call it, in the old days, free will. Mm-hmm. Today we call it decision making. Mm-hmm. So now we have, it's a very popular topic these days. People are trying to find home, a structure or mechanism in the brain for decision making. Mm-hmm. And this is based exactly on the outside-in thinking, because without the decision making, there will be no translation from perception to action. Mm. So this is the fundamental problem. Mm. Philosophically, we can make up another problem, not make up, but it exists, that neurons in my brain have no idea about the objective reality. Mm. They don't see the rows. Mm-hmm. In my visual cortex. All they see is action potentials coming from somewhere else. Mm-hmm. So if that is the case, then how do we make neurons smarter? How do we make neural circuits smarter? How do you ground that input that is given to the brain and give some meaning to it? And then you can start thinking about, how is it possible? What else is there? How you can ground? And grounding typically means you compare something with something else. Now, if you don't understand Chinese characters, but you speak English, then you need a grounder, which is a dictionary, and you go from one symbols to something else, and through the correspondences, you ground them. Now, in my view, the only other thing that exists besides what comes in is action. That is how you can manipulate the world to change it and learn different attributes about it. A simple example is when you put a stick in water. And, it's an old illusion that everybody knows that it looks broken. And then you can have millions of other things. You can use AI if you want. You can use 5,000 cameras to figure out whether the stick is broken or not. But no amount of information about sensory inputs will give you the right answer. But if you start moving the stick, immediately you've got the answer that it's not broken. So that's the fundamental difference between what you can call the outside in and what I call the inside out.
Is this simply not to make it too reductionistic, but is this just simply a framing issue, right? That the outside in is a framework. It's a philosophy of sorts of how we understand the brains inside humans and how they interact with the natural world. Whereas the framework you're proposing is just kind of the opposite, which is, okay, how do we work from the inside, kind of out, and we say, okay, how do we build up from that to then get all these things? And as you're saying, where is the home for all these things that sit? Is it simply just a framework issue, or is there something more important that is there? I suspect that the action piece or the utility of why the framework matters is, I guess, the most important here. But what's the kind of high stakes, if there are, of kind of these opposing frameworks here?
Well, if you want, it's simply a framework. Mm-hmm. I don't say anything else. But, everybody knows that the world is flat because this is how I see it. This is how you see it. And what is the difference between looking at the world as flat or it's not flat? It's just a matter of the framework, right? But it comes with consequences.
Yes, they can, certainly. You'll find out very quickly if it's flat or not if you try it.
Exactly. Or even just to say, okay, the center of the universe is our planet.
Uh-huh.
The center of the universe is the sun.
Right.
That's just a big, you can say it's just a little change. And it's interesting only for academics. But in fact, it comes with consequences because then you formulate the questions very differently. And the answers you get and the interpretation you get will be very different.
So,
and many times when I have, and I talk to people like you, they ask me and said, okay, what are the consequences? Why don't you tell me in 5 sentences? Well, it's true, but that, I should tell you the alternative. But when you have a different view, such as you say that the center of the universe is not the Earth, then you don't immediately have all the answers. But you start thinking about it in a different way, and on the way, you provide a potentially different answers. Now, is it the right framework? Who knows? Is it a different way framework? We know. So the difference in looking at things gives you a richer information, and that's all I claim.
So can we, I guess, this is sort of a kind of a footnote to this question here, but I guess it kind of can summarize a few things. In the book, you mentioned a bunch of different, kind of a history lesson of sorts. We have William James, we get to cognitivism, behaviorism, Gestalt psychology, so on and so forth. And they're using mostly this outside-in framework. Is that just a kind of, that's what people do as they're developing science, is they keep moving through, as you move through time, you build off what the last guy did, and then the last guy or girl, and then you say, okay, well, we're learning a little bit more. But do you think that sometimes we keep the outside-in framework, or we're maybe more reticent or resistant to other frameworks, maybe an inside-out framework, because we kind of get used to the ideas we like? It's like, well, this worked for William James, and it worked for Skinner, and it worked for all these folks. Then it becomes not a taboo, but it becomes kind of like, yeah, but we know so many things. And if you, chip away at the legs of this kind of framework, then maybe all those things we think we know aren't true or something like that. And I don't think that's what you or anyone say necessarily, but is that maybe why some of this happens, is we kind of just get comfortable with the frameworks we have?
Of course. So as I started our interview, that it's impossible to find nothing in the brain. So if you are working diligently, the brain is a terra incognita. There are so many things that you can discover, even if you don't care about the big picture. And you can continue doing the same kind of experimentation. You can continue interpreting the findings in the old framework, and we are getting richer and richer and richer. But you can ask the question, you may see it in my book, I attack, if you want, the very best people in neuroscience. Not because I disagree with them, but because they generated the most progressive thoughts within their framework. So Hubel and Wiesel, who continue to be my heroes, they did what was the best in their framework. But then at some point you can ask, how many more cats and monkeys and how many more neurons we need to record from, and how many more pictures we have to show to understand vision. And at some point you conclude that even infinite is not enough. Because vision is not about perceiving in the traditional way, that absorbing what's coming out and finding a correlation between what's coming and what comes out. So as I said, this is the traditional input-output kind of framework. And the funny thing about this is that it makes sense only for the experimenter. Because the experimenter is in the privileged situation, because the experimenter sees both the outside world, the lines are moving or the rose is shown, and what happens in the brain, either using single unit, multiple units, Bolt signal, whatever you measure.
Yeah.
And then you are in the privileged situation to see the two, and you can do correlations.
Mm-hmm.
Now you can do better because you say, okay, now I understand the code of the brain, because what we can do is take 90% of my correlations, making a model, and then next time I just use 10%, and I can convert back from brain signals what the brain should be seeing.
Mm.
But that's an illusion.
Yeah.
Because that requires the experimenter.
Right.
But the brain itself doesn't see this. So that's the fundamental problem. And therefore, going back to the Hubel and Wiesel approach, and it's not only vision, but in general, this is the sensory physiology. If you look at famous books like the Kendall book,
mm-hmm.
This is a huge Bible for neuroscientists.
Mm-hmm.
I don't want to make a percentage, but a large fraction of it is about sensory systems.
Yeah.
Because it follows the medical books,
mm-hmm.
medical physiology books. Kind of this discussion is that you have to look at the bones first, and then the muscles, and then the intestines, and the hearts, and all sorts of organs. And the same thing happens in the brain. We just go and sensation, and then the problem when you would like to bring it together, the student gets to the exciting chapter and finds nothing, or very little, about the most exciting questions, right? And then you can say, so why is it that we dedicate so much of our effort to understand our cognition, our mental life,
mm-hmm.
and we know so little? And maybe that's the reason.
Yeah, it's very, very interesting. I like everything you say there, and I agree. So we've kind of been sort of mentioning it here, so maybe you can spend a little bit of time is on this idea of understanding causality and self-causation in the brain, and how you see causation as problematic in self-organized systems. If you want to tack onto that action and perception, you can as well. But how do this concept of causation, you see is a sort of an issue. Could you talk about how you see that as problematic for self-organized systems like the brain?
If you look at an open system and you change something there, it's pretty easy if you are looking at locality, then what happens in locality.
Mm-hmm.
And then you can say, a ball is hitting another ball, and the second ball is moving. And there is no question that the cause of the second ball moving was the first ball hitting.
Mm-hmm.
Now, when you look at a linear system like this, then it works very well. And you can go back to Aristotle and say, post hoc, ergo propter hoc.
Mm-hmm. Mm-hmm.
That happened earlier. Something happens earlier, so later, the cause has to be earlier.
Mm.
Now, in systems that are organized in a very complicated manner, such as galaxies,
mm-hmm.
or at the microscopic, nanoscopic level of organization or chemistry, where there is or you come to biology, where the causes are often hidden, and there is not one cause. And we know that from Pearl's famous book about multiple causes, and then we make up additional terms. We said, okay, complex causes and sequences of causes and so on. And then you say, yes, how far you have to go back in time to find the cause of current problems in Ukraine or current problems in the rest of the world. Now, what was the cause? And then you face problems that says many of these steps are embedded into a larger and larger and larger onion-like organization.
Mm.
And that's the problem in the brain also. You may know the famous Van Essen diagram. It's a hierarchical system. It starts with vision, it starts with the retina, and then builds up. It's a beautiful thing, and it's our favorite picture because the hippocampus, our favorite structure, is on the top.
Mm-hmm. Mm-hmm.
And it has arrows from the rest of the brain. It has no arrows anywhere. But you can redraw that picture the way I redraw it in my book and several places as loop, 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 loop upon loop upon loop. And that's what happens. That's the reality of evolution. You know, the brain didn't grow in a hierarchy. The brain grew in or evolved in loops. And then when you have the loops, then you say, okay, I can do a perturbation. And I see consequences. But is it really the cause that I'm interpreting as interpreting the consequence? In a sense, yes, because I know that I did the perturbation. But going from one level to the ultimate level, let's say behavior, figuring out where is the cause, the real thing, is super problematic. And, you know, when you take a logic class, which I did in high school, we were told that, you know, what is causation and how you make inferences and things like that. It works very well in a clean system. But in many other philosophies, it doesn't work, and that it's not even needed. You know, Far Eastern philosophies don't even use the term cause. They use something which could be translated as meaningful coincidences, such as, you know, we had a little flood in New York a decade ago. And what was the cause? Well, it was a coincidence of many things, such as the high tide happened to be at the wrong time, because this is when the wind from the south and from the north met around New York City. So, where do you put your finger on? And I said, which is the ultimate cause? Or you can say, no, that is not the ultimate, it's a complex cause. But then you are washing away the problem. So what I'm saying is that, yes, of course, we do perturbation experiments all the time. This is our bread and butter. Optogenetics is one of the main things that we are doing. But we don't call it causal neuroscience because it's not what it is. It's how it is marketed. In fact, we do a perturbation, and through perturbation, we can make understanding, but it's not as simple as it is advertised.
Yeah, basically that there's, you know, multivariate pieces here, and you always have to, place as a starting point. You're choosing to place a starting point there, but there are things that come after, things that come before, things that are on the edges of things, and you're deciding if this is the cause and here's the effect. But there are so many variables that are contributing before that event, after that event. So, you know, this kind of clean, as you're saying, linear component to it is maybe not as it seems, if you will, especially in the brain as well. With perception, I guess. So you talked about this a little bit, that you look at, neuroscience textbooks and many physiology textbooks and things like that. And we have this, what we know in the world is through our senses, right? And we're very preoccupied with the senses and how we perceive things and things like that. But you have some different ideas about this. So when it comes to perception from action, how do we connect through the world by action and not just solely by our senses, as many people say? How is there this kind of active sensing of sorts for perception, if you will?
So maybe we can connect this to the causation problem, which is, I often give this example that you're driving on the highway, you hit a deer. That happened to you, I don't know, it happened to us. And then you interpret it. You said, what happened is that there was a deer, I see a deer, I slam on the brakes, the airbag explodes, and you give the story. But in reality, that's what happens. What happens is that there was something, you slammed the brake, and then you saw the deer. And the reason for that is because there are loops and loops and loops and loops and loops. the brain is organized in such a defensive manner that if something unusual happens, such as a quick sound, when for the first time you are listening to Handel's Messiah, and all of a sudden the drums come in with 130 decibels. Then all of a sudden you've got a startle reaction. That startle reaction is very, very short latency. It's at 110, 120 milliseconds. All it requires is the brainstem. It is too short for perception. So perception comes a little bit later, but you already reacted. So here, the interesting thing is that things happen earlier than the cause, and then the cause and time and so on, then you have problems with it. And then our crutch in this interpretation, of course, is time.
Yeah.
As a belief that time is an arrow and it goes in one direction. And we can talk about it later. But it is a perfect example that, how is perception, how we interpret the brain, and how we learn about things, and how we interpret the findings. And we have a tool to interpret things, but that interpretation gives you wrong interpretation many, many times, as many of the tricks of sensation prove to us. There are many illusions that are difficult to interpret it otherwise, and it's just simply because these illusions are given to a brain that are not functioning in that niche where we belong to. And it's not a shortcoming of the brain. You can make billions of illusions for a frog brain or a bird brain, and it's you can call it illusion, but in fact it just explains you how their brain works. So now, how do we use perception? And then I try to contrast it to what I call the primacy of action. Now, many people, including my good friend Rodolfo Linas, said, they emphasize this, that you can survive in this world if you are a small creature and if you are in the right environment just by swimming around. That's action. And your chances of getting food, if you have nothing else, just opening your mouth, and then by chance, food will come to you. Action or moving around and exploring the world is useful. But without action, without the ability to move, sensors are useless. Now, what is the point of perceiving the world in its beauty if I can't do anything about it? What is the usefulness of feeling a burning feeling if I can't react on it? So obviously, perception becomes percept through action, because you do something with it. Now, it doesn't mean that action alone can help you, but you add sensors to a developing or evolving brain. Once it can be a partner for action, because the entire goal of your action is that the brain knows about it and then tracks the consequences of the action. And you can track the consequences of the actions more effectively if you have sensors. But you have to have the ability to react, as well as the ability to know that you are the agent, and it's an agency-driven change that you are seeing. Now, going back to the perception-action cycle and the action-perception cycle, traditionally we think that there is a loop from the world, perception, decision, action. And this is the arrow. Now, the funny thing about action is not only that every action system in the brain that sends something out from the brain to the body in terms of controlling your body or your muscles, but it also controlling your heart and respiration, which is the autonomic nervous system, or sending out hormones or substances that can have a slow effect. Every single effector system, so to speak, sends a message back to the rest of the brain, including the sensory systems, that I am the actor of my actions. This is called the corollary discharge, a great invention in the nervous system organization. Because this is the only way how you can tell that the world is changing because of your actions or because of something else happening. Now, for me, in my world, action is all the effector system, including the thought. Because you can ask, what is the thought? You have thoughts, I have thoughts, everybody knows that we have thoughts. And you can say the thought is nothing else but the synthesis of knowledge. Not quite, because if you don't have a ability to act upon your thoughts and verify and ground your thoughts, you don't know whether your thoughts are real, quote unquote, or you are schizophrenic.
Right.
So we have this ability that we generate actions and register the consequences of the actions. Now, this is a good framework in my world because it explains the utility of every brain, small or large. So, in a very simple organism, the nervous system that it has can predict the future or the consequences of its own actions in a very organized, small niche in an environment into which the animal evolved into. And at a short time scale. Now, you add complications to the brain, more and more loops and so on, but the entire goal of this complicated hardware is, again, nothing else, just predicting the consequences of the creature's actions. But now in a more complex environment, which requires higher flexibility and at a much longer time scale. Now, you can go all the way to the thought. It said, well, what is thought then? Thought, for me, is a delayed action. Or not a delayed action, it's an action that can be utilized in the future. Because I think about something and I translate my thoughts into something. If I'm not able to translate it and test them, then the thought has no meaning, no utility. So again, you can say you can go from the synthesis all the way to the top, and that's a complicated process thought. Or you can say, no, it's actually a way how to generate an insight. What will happen if I have a stick and a stone tied together? And I can make that action in a way which we call internalized action. And then this is the only way. Other than that, there will be a trial and error, trial and error, trial and error. And we know that other animals are not making tools a lot because they don't have this ability to play with this action. So this is what, tool making is an example of externalization. I talk about externalization of brain function, which is today's a big thing because we have AI. That's the ultimate externalization of brain function, perhaps.
Yeah.
But there is also an internalization, which means that initially you have to calibrate the brain and you know what would happen if you do this and that. But now you don't have to act out because you have done it. You already calibrated your brain. So this is where people again pose me the question, said, oh, you don't have to move. You just think. That's true, but your brain is already calibrated. And then you can do a trial and error. So what if I do this? What if I do that? What if I participate in Xavier's podcast versus enjoying the scenery around here or do my homework? And then you look at and put it into a possible scenario you evaluate them internally, and then you act and say, yes, I will do it. So this is a little change in the framework, but with long consequences, because then I know where to start, how to do experiments in the laboratory, and how to find other people's findings and reinterpret them within this framework and find what's wrong with the interpretation, or how can that interpretation be substituted with an equally good one in another framework.
That's very interesting. The way you mentioned it there about the thoughts with actions, you were giving the example there of it was very, very fascinating. I had never thought of it that way. And it's kind of hard to not think about that in the way you described it, which is very, very interesting. As I was listening to you talk, a lot of this stuff sounds, and you mentioned at the end of the book, but a lot of this sounds very similar to Bayesian brain, predictive processing models. Again, just maybe as a footnote here, how much of the inside-out framework that you're describing here, particularly with action and thought and perception, but just generally, how much do you find there is overlap, or is there a lot of divergence with the kind of predictive processing, Bayesian brain kind of models?
There is nothing new under the sun. you can always find analogies, and then no matter what you do, said, oh, this is your framework is like, because this is what the brain does. The brain always compares. I cannot show you anything in the world. I cannot give you any theory that you say, I have never seen anything like this. Even if ET comes to the world, we will say, oh, it is like, because we do the grounding. And it says, no, it is like this. So yes, in fact, the inside out, Jerry Edelman, who was one of my good conversation partners when I used to work at UCSD. And later on, I was part of his club. And we had fantastic discussions. And when I take one view, he takes another view, just for the sake of discussion.
Right.
So then you can go back to deep philosophy, and you can say that there is always a predecessor. Or you can go fast forward and say, you ask in your email about Carl Friston's free energy principle. So yes, probably we are saying the same kind of thing. For me, Carl's free energy is basically a mathematization or mathematic description of what the brain fundamentally does. And what the brain fundamentally does for me is that, again, it's not my idea. Perhaps I could go back to Sherrington, and before Sherrington to Craig, the psychologist, who said there are fundamentally two behaviors. One is what they call preparatory behaviors. I can call them exploratory behaviors. And then there are terminal behaviors, or they called it consummatory behaviors. Now, consummatory behavior in the Latin translation is not consuming only, eating, but everything else that is the end of a exploratory action, such as sleep or immobility. Okay, so the reason why the brain is the brain has two states basically is because one is about exploration, movement, moving forward, with one goal, which is terminated. You have to, in the teleological goal, you found a goal, and when the goal is found, you switch the brain state. In the hippocampus, it goes from theta to sharp wave ripple state. It's a switch change. It's a brain beautifully describes this change. That never fools you. It's absolutely reliable. So then you go from one state to another state, and then it changes. And now, this brain shift from going from one, there are two algorithms, and without two algorithms, you don't get very far. Now, you can be in an alert state forever under the effect of amphetamines, for example, and you have the illusion that your brain is vivid and you are learning a lot, but next day you fail the exam because you don't remember anything. So in order to remember something, you have to switch the brain state into something else. And then this switch from one state to another can be achieved by the brain itself when it explores the unknown territory, or by an experimental manipulation that we do in the laboratory all the time, which is giving a piece of food or reinforcement. So the reinforcement idea and the decrease of free energy and so on, it is based on this experimental paradigm, which is a particular thing only. It's a smaller part of a larger picture, that reinforcement is helping you to switch from one state to another. So now we have reinforcement learning, which is a big cottage industry, because within that framework, everything can be described. But, and here's the but, with the help of the reinforcer. And in the framework, especially in the artificial networks and in the mathematical equations, the reinforcer is a human manipulation that comes from outside.
Yeah.
And the brain can do this switch with itself. That doesn't require a reinforcer. Now, we go back to the beginning of our discussion, saying that, okay, now we have another word, reinforcer. And that could be related to things like signals and stimuli. So these are the three pillars. We talk about these three things, but there are no stimuli in the world. There are no signals in the world. And there are certainly no reinforcers in the world. There is nothing in the physical world that is reinforcing anything. Reinforcement is a relationship between something out there and the state of the brain. Now, sugar is a reinforcer for cockroaches and humans, but it's not a reinforcer or pleasure for many. Dogs don't like sugar, or cats certainly don't like sugar. And so there are many of these examples that it's not the physical thing that it makes the reinforcement or reinforcer. It's not reinforcing anything, and it changes. If I have, I'm willing to walk a mile to get a good ice cream, but after consuming 5 pounds of ice cream, the same ice cream is aversive. So it's no longer doing what it does, and that's the same reinforcer, if you want, because the same physical thing. And unless we understand that, then we don't get far enough. And so, in my world, reinforcement is a opportunity or an affordance to change the brain state. And once we can do the manipulation, that this is what we do, and this is what we do in reinforcement learning, and this is what we do with the experimental methods, that we know exactly where the brain state changes. I can do it without knowing anything about the world, because not I, but we, many of us, because I can put an electrode in the hippocampus and I can know exactly, precisely when the brain state changes. And does it matter whether it is the brain change happened with the help of a reinforcer, which we can't call reinforcement, or the animal is exploring the environment and it stops here and then moves and stops. And every animal that has been studied follows a leave flight. Leave flight means basically a random walk. If the animals were exploring the environment without stopping, they would learn nothing. So this is a fundamental brain feature. AI hasn't discovered it yet in its entirety, that this is something absolutely needed for the brain. It has to run two different things, because it has to explore. It has a limited capacity perhaps for putting things in, and then it has to switch. And the switch is typically what we refer to as memory consolidation.
When you talk about this reinforcement piece of it, it's really interesting, because I've asked this before. I'm curious of your thoughts here. Is what do you think about that? Again, this is sort of a tangential piece of it, but I think it might be important. I'm saying that you're an expert on this, but in terms of the brain of sorts, what about for folks that let's say have addictions, right? And you'll see these things about addictions in the brain and all these dopamine drives and all this stuff. When you talk about, when you think about like rewards, right? Certain rewards that people will feel. So if somebody's an alcoholic and they have a drink and there is a reward system for the brain or whatever, how does that kind of work in your framework of like, well, the alcohol isn't a reinforcer necessarily, right? So is it just trying to get reward? Is it more of just whatever's salient in the mind? How do we conceptualize it? I guess this is a little bit more clinical, but how do we conceptualize things that we typically see as reinforcers for people that could be negative or positive? How do we have in this framework that you're pushing here? How would we conceptualize that, I guess?
Well, in a simple and perhaps primitive and not very helpful way, we can say that we derail the normal physiology. We do something with it, and then we are using the same exact niche within which the brain is no longer functioning the way it did before. Now, when I use a needle and prick myself, it's painful. I hate it. Many people shout and so on. But then it gives me some amphetamine, or let's say angel dust. Something that will change my brain state. Right. And then all of a sudden the needle becomes a goal.
Yeah.
And a positive thing. So you go from extremely negative to extremely positive. And what changed is probably some gain in the brain that I can't explain easily. And people like to say reinforcer. And now the reinforcer is substituted with dopamine.
Right.
And just for the record, I have admiration to reinforcement learning and the people who are cultivating it. And I have extraordinary respect for dopamine. But dopamine is a dumb substance, and VTA, ventral tegmental area of the brain, where the neurons, dopaminergic neurons are releasing it from, is a dumb, simple thing. It doesn't make decisions for you.
Yeah.
In fact, if you look at this is something I like to ask from people who are believers in dopamine reinforcement and so on. Why there is not one dopamine neuron?
Right.
And why does the number of dopamine neurons in the mammalian brain scales with the size of the brain? Why do we need more dopamine neurons in the brain of an human being compared with a mouse? And there are many examples of this. The pre-Bassinger nucleus for respiration, all subcortical neuromodulators like dopamine, norepinephrine, acetylcholine. All these systems are neuromodulators. They only have one function, is just to change and modulate things up and down, providing some gain. But why there are more neurons? And then the answers I usually get from molecular biologists, there is a size gene. You just can't help, when the brain is bigger, then you just multiply the brains by some ratio and so on. My attitude to that is that, no, the brain has a loop organization, and every single time you add another loop, it has the requirement, or it has the utility, or whatever name you give it, to have access to everything that is downstream, to the lower loops. So when you have a larger brain, all those larger brains would like to have access to the respiration neurons, for example. Respiration neurons don't only do in and out, in and out, in and out, inspiration and expiration, but that allows us to speak, sing, and so on. So we can change respiration at any time. In order to do that, my motor cortex, my supplementary motor area, my basal ganglia have to have reach to the respiration neurons.
Right.
The same applies to dopamine neurons, that the VTA becomes smart because of its efferents that it receives from larger areas. So it looks very smart in a monkey because it has many, many connections from the smart areas, which are the cortical areas, because they you can have access to them. So this is the way how you can look at it, that it's a loop. It's not only that the medial septum is projected to the hippocampus and provides cholinergic innervation, but it's the hippocampus that goes back to the medial septum, goes back to the basal forebrain, and so on. And then there is a circular control. And this is how we should approach the problem. And then all of a sudden, the reinforcer will be a funny thing because it will not be the cause, but it will be part of a loop whose entire understanding is required to understand how the brain works. Now, going back to your question, after this long
that's all right.
preamble, if you change this gain a little bit, then there are consequences. So, for example, when you are obese, and because you have type 2 diabetes or something like that, then you don't do a lot of things perfectly, such as you don't sleep well. And the answer is that, you are obese, therefore you have sleep problems. Well, we just had a paper 2 years ago where we showed that maybe it's the other way around. What happens is that your blood sugar level can be controlled by a complicated mechanism. And if you change something with that, then the brain goes in a wrong direction, or the circuit is altered. And the first readout of that altered thing is sleep, because sleep is an honest state. If you are investigating and comparing the brain of a schizophrenic or depressed person with a normal one, the inside out is better than the outside in, because the person is not interested, the person is disinterested, and so on. But during sleep, you look at the dynamic of the brain in its true beauty, and you can see the alterations. So from this perspective, you can say, what if I change the gain artificially? We can do it with optogenetics or something like that. It's that, hippocampal patterns can be affected by dopamine, but perhaps the other way around is also true, that if I can artificially change, whenever there is a particular pattern in the hippocampus, I pump a little bit of dopamine into the system 2,000 times a night in a closed loop manner. So the sharp wave ripple that we are obsessed about as a memory consolidator mechanism, that can be used as an input to a artificial system, and then it can switch on the activation of dopamine neurons. Now, we haven't done the experiment, but you may wonder what happens if you now connect things that are not connected normally, and then you wake up, and all of a sudden, the gain of the system in this will change. And maybe everything will be absolutely positive. You look around everywhere, and because any little tickling of the dopaminergic neuron will release a lot of them, and then you become happy, or the other way around. And so if you look at it from this perspective, then indeed there is a good way. In fact, you asked me about how far we go back with the inside out. In fact, there have been ideas about schizophrenia as a disorder of the corollary discharge going back to the 70s, because that's the corollary discharge is what provides you the reality in your niche. But if you change the gain, either in the world or you change the gain inside the brain, then there will be a mismatch. And that mismatch is what causes problems.
Yeah, it's very, very fascinating. And I think it's important because a lot of these things can maybe potentially, sometimes the framework can help change some of the outstanding questions we have on certain things like schizophrenia or certain sleep patterns. So, okay, I want to give you as much runway as you want, because this is kind of your space here on the hippocampus. So many people know the hippocampus is involved with memory, especially working memory. It's not all it is, and so you've done lots of research on this. So in the book, obviously, you talk about, I think it's in your previous book, but it's mentioned in this one too, the importance of brain rhythms for neurosyntax. You can chat about that. And also there's this really interesting bit in there about maps, place cells, fields in the entorhinal cortex and also talk about the hippocampus, the thornal system, and how that connects with the neocortex for navigation and direction, which I thought was very fascinating. So you can tackle any one of those in any way you want, whichever makes sense in terms of the layout of the question here. But tell us about how the hippocampus and how brain rhythms are implicated for understanding many things, such as navigation, direction, sleep, things like that. Just tell us what's important within this framework of understanding hippocampal volume or the functionality or whatever.
Oh, let's talk about rhythms first. So the reason why you can understand me, despite of my accent, is because your brain has the same constellation of oscillations as mine. Mm. So you emit things in packages of information that my brain is made to perceive. Mm. And if you would like to send information through other means, such as a Morse code, you have to decide, what is the basis of communication. Mm. Now, communication in the brain or anywhere in any system is basically an agreement between the sender and the receiver. Mm. There has to be a cipher that is known to both parties. If there is no cipher, then there's no information, because information becomes. There is nothing. There is no information in the sendage. As Shannon already declared early on, that information is about translating it. Mm. Now, the difficult thing in messaging is that how you break up a very long stream of stuff into manageable chunks, such as language. Mm-hmm. Then we break it up. I have an entire thought about the world, and I write it into a book. But then there are book chapters, then there are paragraphs, and so on. We go back to the sentences and words, and then phonemes, and so on. So in Morse code that I learned earlier, the biggest problem learning is where are the gaps? Hmm. That is, where is the beginning and end of the message? Because if there would be no end and no beginning, then it would be just a continuous stream of tita, 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 and it would be the disaster. Nobody could decipher it. Mm-hmm. In the brain, it's even more complicated because there are bursts. You can say that's the da, and action potentials, a single action potential is the tit, but their action potentials are pretty much the same. So you need to have a way of how to break up information. Mm. Now, what is the beginning and the end of the message? And the best way to do it in the brain is through inhibition. Mm. And everybody who studies the brain recognizes that inhibition is such an important invention. There is nothing like inhibition in the physical world. There are forces against forces, but that's not exactly what inhibition does. It's against control and things like that. But every single brain oscillation that we have known, at least in the range that we are studying them, is based on inhibition. So inhibition is a natural way of packaging information, and it is reflected by brain oscillation or brain rhythms. So we can call it the neural syntax, because this is the syntactical rules are providing ways how in a short time, such as the gamma cycle, 10 to 20, 30 milliseconds, you can package information. And then the entire goal of putting a lot of neurons into this time scale is nothing else, just to have an impact on a downstream neuron. Now, the downstream neuron has a membrane time constant, which happens to be 10 to 30 milliseconds for pyramidal cells in the mammalian brain. So within this time constant, the neuron can integrate. So the entire goal of bringing together neurons into 10, 30 milliseconds or in a gamma cycle is the ability to send a message, which is read out by the spike of the receiving neuron. Now you can say, that's good. This is the fundamental organization. Indeed, this time constant is interesting because this is also the time constant of the GABA A receptor, the AMPA receptor. This is also the funny time window of spike timing dependent plasticity. There are many things that come together in this range. Now this is okay. Now you've got 1 bit. Now how you put together from bits to many. And then it turns out that when you look at the hippocampus first, but then it was true in other systems also, that hippocampus has gamma and then it has theta. And then we observed that the gamma is not independent of theta. In fact, there are about 7 plus minus 2 gamma cycles in a theta cycle. So now you can concatenate shorter messages into a longer message. And then it's a general rule that we described, and many people contributed to it, that there is a system, a hierarchical system of brain rhythms in our head, which has a fundamental rule, namely that the slower rhythm, or the phase of the slow rhythm, biases the amplitude of the faster one. And then the phase of the faster one biases the amplitude of the even faster one. And it goes on to multiple levels. So, for example, we have a very slow oscillation that every minute it repeats, both in the periphery as well as in the brain. It's most prominent during sleep. This is called the microarousal pattern. So during non-REM sleep, there are microarousals, and then they happen about the same time. If you look at your stomach movement, that happens at the same time. If you look at the movement of blood, that's also about 1 minute or so. So the entire body, including the brain, has this oscillatory pattern. And then this 50, the 1 minute cycle, modulates another one that happens every 10 seconds or so. So 0.1 hertz. This is the famous bald signal that you can look at the fMRI, and when you look at what happens within this framework, you can say this is the default network and so on.
Yeah.
So this is another one. So the very slow one, we call it ultra slow, modulates in phase the power of the infraslow, which is the bald signal. And then it changes the so-called up and down state or slow oscillations during REM sleep. Now, the up and down states in the neocortex modulate the number of ripples in the hippocampus. Now we are at 200 hertz. So we went from very, very slow, 0.02 or 0.01 second to all the way to about 200 hertz. So there is this hierarchy. So this is good because now you can package information, and it's relatively easy to share the cipher, because the cipher is the brain cycle, the oscillation cycle. So as long as the neocortex has information about the theta cycle, it can read it out. Now, here comes the complication. The hippocampus and the neocortex are not point sources. They are structures. And things happen in time. They happen in a theta cycle, for example. That's about 120 milliseconds. But in 120 millisecond time, things happen also in space. So the translation of this is that at the beginning of the theta cycle, the activity of the dorsal hippocampus is here. And then it moves to the ventral hippocampus. And it takes about half a theta cycle, or 70 milliseconds. Now, the neocortex, the reader of the hippocampal message, is also not a point source, but it's also a huge cortical mental. It's some topography. So it has to know not about what's coming in now, but what will coming in later, or what came out earlier, and it has to concatenate this message in space and time. And now, with that, we come to the problem of space and time and the hippocampus. Are you ready for that?
Yeah, I was going to ask about this. So I heard in the book, and I'll be honest, I couldn't quite connect it in my head when I read it. But now that you're saying it, it's making a lot more sense. Yeah, how do we see, specifically with the oscillations and in the hippocampus, and maybe I'm sure there's obviously, where this is, spreading throughout the limbic system maybe as well in the subcortical region, but how do we understand how space and time moves or works within the hippocampus? I am curious about this explanation, because it was interesting the way you framed it.
Me too. So you go to the airport, and then you can ask the question in the airport. It said, "Oh, what flights are coming in the next 2 seconds?" Right? And then you say, "Oh, there is one from Alaska, another one from Paris, the third one from Abu Dhabi, and so on." Or you can ask, "When are the planes are coming from Paris?" This is a different question. You are point source now, because you are interested in about the Paris flights. Mm-hmm. And the Paris flights are coming in at different times. And at the same time, there are different flights coming from all over. So this is the same exact problem, because now you have, if you would like to understand the entire traffic at the airport, you have to know about the entire time frame, mm-hmm. and about the space out there, mm-hmm. where the incoming flights are coming. So this is the analogy to my problem. Now you can say, that's good. So let's go to the hippocampus. What does the hippocampus do? You read the New York Times, and it says it's the GPS of the brain. And this is about spatial navigation and so on. But again, this is a very interesting thing, because the GPS, there is no time. First of all, there is no space. There is no distance. GPS is based on phase differences. It's just a slightly different thing. But from the neurobiological problem and the psychological problem was what we started with, is that memories are understood, especially interesting memories such as the episodic memory, because it's a declarable memory that we verbally declare. So that was number one problem. The second one, this was a beautiful formulation by Enver Tulving, who says that episodic memory is what happened to me where and when. In other words, everything that happens to us happened somewhere.
Yeah.
And therefore, we have to know the where. And it happened sometime. Mm-hmm. We need a timestamp on the arrow of time. Mm-hmm. And again, from the outside in framework, this is a beautiful working formula. This is a roadmap. This is what neuroscience have to do. Neuroscientists have to go and figure out the what. Neuroscientists have to figure out the metric of the where and the metric of the when. Mm-hmm. And then when you have the three of this, then you can combine them all the time, and then you can do what Enver Tulving postulated, you can do a mental travel. Mm-hmm. So the way how we thought about this, that in a way which is questionable, but at least it shows some progress of thinking, is that how come that in one textbook you read about the hippocampus as a GPS, and in another textbook you read about as the source of episodic memory? Mm-hmm. What the heck is the connection between the two? And one is about space and time, the other one about perceiving the world in space metric, but action is needed for navigation, because navigation is moving around space and time, if you want. So this is one little problem. So our solution was this. Navigation has been worked out as a useful mechanism in the animal's niche with the help of outside cues. You know where to go because there are landmarks, and there are temporal and spatial relationships between you and the goal, and so on and so on. So then we said, that's an interesting navigation. But as we learned from Enver Tulving, memory is mental navigation. So what we have to do is now disconnect the brain from the rest of the world, This is what we call internalization. And then we can travel forward into the future or backward into the past and use two different words. We don't use navigation. We just use postdiction or prediction or memory and imagination or planning. So there are different words, but they refer to the same algorithms. And in fact, one presumes the other. You cannot imagine anything without memory. You cannot plan anything without your past experience. And in the hippocampal theta oscillation, when you can, in 120 millisecond, you can play a segment of time from what happened behind you and what will happen in front of you. And this segmental change shifts back and forth, back and forth, back and forth. And there is no place where I can put my finger on and say, this is now, this is the past, and this is the future. The whole thing is just one thing. Okay, now you are in deep thought. I can see your face.
Yeah.
How does it relate to the problem of episodic memory? So I said, wonderful, because now we have three axes. We have to look for space and time separately. And in fact, that was the welcome of O'Keeffe's beautiful discovery of the place cells. That, okay, now we found not only the what, but we found also the where, because now we have a metric for measuring distances. Now, where is the time? And now it was my good old friend, who unfortunately passed away, Howard Eichenbaum, who looked at one of our experiments and took it very seriously. This is an experiment where we ask, what happens when you freeze an animal in space and time, but ask the animal to remember something. And then we confronted the prediction of the space theory or the episodic memory theory, if you want, or the spatial navigation theory, is that there should be, according to the theory, there should be neurons that always define the here and now. So there should be a subset of neurons in the hippocampus. If the animal is not moving from anywhere, is moving, but not translocating in space, there should be a subset of neurons that will fire forever, as long as the animal is in the XY coordinate here. And all the other neurons should be shut off. So we have done an experiment where we trained the animal to learn that you should remember that you came from the right in a maze. Now, next time you have to go to the opposite direction. But in the meantime, we ask the animal to run always in the same direction with the same speed. So from our perspective, from the animal's perspective, the world didn't change. It was constant. The internal state of the body remained the same. So we were looking for these special cells, and we found not one. What we found is that the hippocampal activity just constantly evolved and changed. And then the neurons were active for about 1 second, and another assembly, and another assembly, and it was a long sequence of assemblies for 20 seconds. We could, in fact, make a prediction about the animal's decision, if you want, 20 seconds prior to the animal's actual turn. Okay. So the animal is here, running in a wheel. I can read out 20 seconds earlier what the animal will do 20 seconds later. Okay. Now, what do I read out? I can read out from the cell assemblies, looking at how they behave when the animal made right turn or left turn. Said I can classify the patterns into two: go to the right, go to the left, and that's the what. But during running, I can also say how long the animal was running in distance. I can measure it. And they said, wonderful, the hippocampus does what is expected, is measuring the distance. But then Howard Eichenbaum said, I can also measure how much time elapsed from the beginning. And he called the place cells that O'Keeffe named time cells. Okay, now we can pause here.
Yeah.
Because now in the hippocampus, there are what cells, cells for the what, cells for the where, and the cells for the when. And the next question you have to ask, who are these cells?
Uh-huh.
What proportion? And then the answer is that the proportion of these cells is experimental design dependent. I can define an experiment, then 100% of the neurons will be place cells, or 100% of the neurons will be what cells, or 100% of the neurons will be time cells. In other words, every neuron can be any of these. Why? Because there was only one type of change in our key experiment, which was a sequence of activity. And the sequence of activity was called by 3 different names. There was one brain pattern, and we named it by the what? Left or right? We called it by distance cells, or we call them second cells or time cells. So now we have an interesting problem, because we had the illusion of finding a structure in the brain and a mechanism in the brain where the where, what, and when came together.
Mm-hmm.
And therefore, we found the mechanism of episodic memory. But we didn't find it. We just found one thing. We called it by 3 different names. And then this is the time when I first started to, touch my forehead and said, my God, there is something problematic here. How does the brain know about space or time? Space and time are abstract.
Right.
If they are abstract, they cannot have any impact on any physical entity, including the brain.
Right.
So the brain cannot perceive time or space. And it also does not make space or time. Clocks don't make space or time.
Right.
Nothing makes space or time. So there is a funny thing here.
Yeah, I'll be very honest. My brain hurts thinking about this. It's deeply fascinating though, because it's like these things don't really exist, but the way we're categorizing them is sort of like that. I guess let me use an example here. What's happening? So there's various pieces of episodic memory. Listeners can do this. If I think back to the glacier I saw in Iceland when I was there 6 years ago, almost 6 years ago, I go in my mental Rolodex, right? My filing cabinet in my head, and I can remember a good amount of it. I can remember what the day was like. It was cold. It was what the glacier looked like. The coldness in the air, who I was with, et cetera, et cetera, et cetera. I can remember that episode in my brain. Is it the fact of, and I can also think about the, trip I want to take to Italy and envisioning things I've seen in Italy, places or movies or documentaries or books or things like that, and what that would be like, and having some idea of how it is in Europe, et cetera, et cetera. But what's going on, what you just laid out, these things are happening in my hippocampus, right? Especially with the idea in Iceland, right? Is there's some type of storage that's happening in the temporal lobes, essentially, right? If it's in long-term memory. But what is the activity, or so we'll go back to the beginning of what you said, there has to be an action here. Like what is the utility or the actionable thing here of my episodic memory within my hippocampus here?
I don't pretend I know the mechanism or the answer to what episodic memory is.
Okay.
But what I know is that you don't need certain crutches, such as space and time, to explain that. Because when you went to Iceland, then you reconstructed the scene that you have seen.
Correct.
But tell me, where is time there? And where is space there? There is no time, no space. You just have events.
Yes.
That are put together in a sequential order. Now, you can argue that sequence is the same as time and so on, but change is what is the fundamental thing of a sequence.
Right.
And change, it's easy to understand because change can occur only to things, according to physics. So change happens to this, change happens to that, and so on. But it's much easier to describe when I say it happened there, and that's a space. It's a point in space, that's Iceland, and it happened then, which is on the timeline.
Mm-hmm.
But the whole thing is a reconstruction. So it is so easy to communicate because we have an agreement about, and we have a metric about space and time.
Right.
Space and time existed, let's say, 200,000 years ago as a vague concept. We talked about the infinity of the universe in both space and time. It not necessarily have these two things. And then we made it a scientific concept. And the way how you make vague concept to scientific is to invent units.
Mm.
Because you can compare something. You can ground the concepts to real things. And the grounding process requires an instrument. The instrument initially was a rod and a clock. We made clocks. We made measuring instruments. And then we can communicate our knowledge to each other because we have a vocabulary, because we have common grounds or a common grounding mechanism. Now, my metaphor, going back to the prediction of where and when the animal, the rat went from the wheel, is that when I'm driving my car and you're asking me, where is your workplace? I can say it is 1.2 million stroke of the engine. And then you are looking at me and said, this guy is crazy. But then I give you another answer, said, oh, it's actually 12,035 revolution of my front wheel. That doesn't make you happier either.
Right.
But then I can use a commonly understood metric and I say, it's 20 miles. Now you know, because I changed the stroke of the engine and the revolution of the wheels into a commonly agreed or jointly agreed unit, which is miles or kilometers. But I can also say it's 50 minutes. And that's communicable also, although you have to know by what means. Am I walking or am I driving? Because then you have this other needed information. But then you know approximately how my actions will be realized and how your actions could be realized if you are traveling with me, because you have the same metric. But it is because your brain is already calibrated with a jointly agreed human-invented instruments. Now, the problem is that mice and rats don't read the clock, and they have no idea about human-made instruments. So what happened, and this is probably the most, how would I say, the craziest part of our discussion is when you talk about space and time this way, said, well, we brought back ourselves to the real problem is that we scientists pretend that we don't have axioms. And my claim is we do have axioms. We have two axioms. Space and time. You take away space and time and our system of thinking collapses. You cannot communicate. I cannot write a paper without mentioning time. Time is the second most used word in almost all cultures. But it is a creation.
Right.
It's an agreement. It's what I call the crutch of human thinking. and it's so universal and so much imbibed into our engraved into our brains that we don't even ask it, except when you do an experiment that I mentioned, and you do experiments along these lines and say, my God, which one is this, time or space? Or what do I do now? What is next? So I'm not interested in philosophy, okay? I just want to figure out what the hippocampus do, but it became a problem. And when you go back in time and in thinking, you have to face these problems. You can neglect them, and you say, it's too complicated, we don't have to neglect them. Or you use your open mind and said, maybe now we can think about this a little bit differently. Now, hippocampus is a navigation device. It has place cells. Everything that we do happens in space and time. So everything that we measure, we give tones and we give lights and so all sorts of things, and we translate them that, the hippocampus responds to this modality. But then O'Keeffe's argument is that, it responds because it generates the gain of a fundamentally spatial system. So he goes back and recently has written a beautiful review about it, saying that the primacy in the hippocampus is about space. Everything is in space. Everything happens in space. That's the primary thing, and you can modulate events within the space. But it assumes that space is real. And then, indeed, the world, the hippocampus, is perceiving space. Now, my alternative to that, saying, no, the hippocampus has no idea about either space or modalities. The hippocampus generates internally generated patterns, pattern after pattern after pattern, many of these sequences that could be utilized after experience gives meaning to some of these patterns. In other words, the brain doesn't read the world. It doesn't absorb the world. It doesn't write or understands the world the way how we think. It's the other way around. We have a brain mechanism which is given to us by evolution, and it's different in different species. And we use that brain trying to make sense of the world outside there. And it just happens that we stumble upon things that happen to be near us or further away us. It takes 2 steps or 5 steps and so on. And we call it distance. So the fundamental difference here is that rather than believing that there is reality there, but whether that physical reality is my reality, and this is the same reality as somebody else's, depends on my action-related attitude to my environment. Does it make sense?
It does. It does. I guess we've been talking about the hippocampus on this. How do we understand these things in the hippocampus with episodic memory in concert with the parietal cortex, the basal ganglia, all of the different aspects we know motorically for space? We have visual ocular motor space, we have visual locomotor space, all these things that we name it that. But how do we see this? The hippocampus is a kind of, a seat here, a very powerful seat for all of these things with episodic memory. But how does that work? We know the brain works together all the time. How does it work in concert with other parts of the brain for understanding space and time?
You're back to square one. The brain doesn't work together to understand space and time. That's my wishful thinking about framework change. That we don't want to understand space and time. We want to understand how the brain works. And the brain works through a interaction with the parietal cortex. It works with the interaction of many other parts of other structures through a syntactical rules that we call brain rhythms and so on. And that is available for the body that it can do things in its environment and then signals it back to the brain whether your desired action was right or wrong. And then we can communicate it to another member of the species or even across species very effectively, because there are regularities in the world. There are recurrences in the world. The reason why brains are useful is for only one thing. It's because there are regularities. There are predictability. There is predictability in the world. If there would be total chaos all the time, brains couldn't evolve. Now, this predictability is getting very, very complicated, as we discussed at the beginning. And that's why we need more complicated brains to navigate our bodies in this very complicated environment. But it's the entire goal is to let the body, the organism, navigate in this complicated environment. If you are a fly or if you are a honeybee, then your environment is a simple niche, and you work and function perfectly for your entire lifetime. But if I capture the honeybees and I place somewhere else, they fail the navigation right away because they are not prepared for something else. But we humans have the illusion that we can navigate anywhere, and we do, anywhere on this planet, and we understand everything, but not quite everything. I don't have a sensor for the magnetic north. I don't see ultraviolet light.
Right.
I don't see infrared. And there are a lot of things that we don't have sensors for, but just part of reality.
Right.
There are I don't feel radioactivity.
Mm-hmm.
and even though there is something real that comes out from emission, but I don't feel it. So my reality is the reality that my brain allows me to construct.
Mm-hmm. Mm-hmm.
And this is too deep.
Yeah,
if you want, but
it is.
But when it comes to complicated things, when not so complicated things, when we are asking about how come that the hippocampus responds to sound, and we have a beautiful experiment which show that the hippocampus doesn't respond to sound. It responds with an action, and the action is what is quote unquote represented in the hippocampus, not the sound itself.
Mm-hmm.
And so many of these things are important because you can fool yourself and say, oh, I found a correlation between this and this, therefore neurons in the brain respond. But there are many intervening variables that we discussed earlier, and this is where the complexity starts. And then unless you are honest and accept it, then you make hubristic claims.
Yeah. Yeah, that's definitely a lot to chew on there. I will definitely be thinking about this. So I guess my last question for you is, you've given us a inside-out framework for understanding the brain. How do we continue to use that, or maybe people in various disciplines, whether it's neuroscience or physiology or neuropsychology, things like that? How could that be helpful? That framework for helping us understand the brain better and how to work with people, whether clinically or otherwise, as well.
Well, it's extremely important, and it's doable. And there are many experiments in my lab that half of the lab members are working within this framework and do extraordinarily nice experiments. For example, just last year we showed that the old framework is that neurons that fire together wire together.
Mm-hmm. Mm-hmm.
So we just inverted this. We showed that neurons that are born together, they wire together and fire together. So the inside out is a very strong thing. Or I can give you another example that is largely independent of us. It was mostly Eleanor Maguire in University College London, that they described that, when we are looking for the structures in the brain that are involved in imagination or planning, they are the same as memory. So all of a sudden, the experimenters were confronted with the problem that the structures, they didn't look at algorithm, but we do look at algorithm, and the algorithms are also the same, or the dynamic is the same. When one person talks about memory, the other person talks about the future, which is imagination. So now it's an interesting thing that we know that it's pretty about the same. We are just using different words. Or I can give you more extreme examples that at least some of my cognitive neuroscientists tend to agree with, that if we would like to see a physical mechanism, we call it a gain. That is, the same input gives you a stronger output that you can measure. And that can be varied. You can increase the gain, for example, such a thing as speed. So the animal is running faster. All of a sudden, the same inputs are generating stronger activity in the hippocampus, let's say. Now, let's go to something else, which is cognition, and say there is also a gain during attention. Attention is a very complicated process also. Mm-hmm. And then you can do a focused attention, and beautiful experiments have been done many years ago. Richard Anderson, for example, showed that all you have to do is to focus in your mental internal life to say, I'm looking at the upper left corner in my mind, but in fact my retina is fixed on the X. And then they showed beautiful gain control, that is the firing relationship between the input and the output changed. So what causes that? And the answer is acetylcholine. When the animal is running faster, it generates acetylcholine, high activity in the cholinergic neurons, and then the acetylcholine generates the gain. Now, through the process of internalization, the cognition can capture the same thing. Now, the cholinergic neurons are not driven from the periphery, but from the upstream, from neocortex and higher activity, and activate those cholinergic neurons, which in turn generate acetylcholine. Now, all of a sudden, there is these two words, speed and attention. They are so different words. But from the point of the brain mechanism, it's pretty similar. So these are the kind of things that I envision that will simplify our negotiations about the vocabulary, because that's how the final arbiter, if you want to summarize our hour-long discussion, I just say, if you are interested in what the brain does and how cognition works, then the brain is the arbiter. No other thing in the world will tell you what is the truth, so to speak, but the brain mechanism. So you have to look at the brain, and the brain will tell you. And in this case, the experiments that you interpret, they said, oh, now I've found a link between a very complicated thing such as attention and a not so complicated thing such as running speed.
Well, it's interesting to see how all of this kind of good science and good research is trying to find, with using this framework, these different ways of how do we conceptualize things that we've seen before already, but then we say, oh, well, this is probably a more, at the very least, an alternative way, or even in some cases, a more accurate way of understanding things such as, attentional capacity or speed or things like that, which is really, really important. Well, György, this was so much fun. I greatly appreciate your time and your wisdom and all of your many, many, many thoughts, which will give me many things to think about. For listeners, of course, he's the author of Rhythms of the Brain from Inside Out. So you should go pick up those as well. And it's absolutely fantastic and very fascinating books. Big thanks. I really appreciate it. Your time and explaining all this. This was very, very stimulating for me. So I greatly appreciate it.
Thank you, Xavier. Let's have another meeting 20 years from now and see what was the impact of our wish.
That's a deal.
And then,
that's a deal.
Then you can make the judgment.
There you go. Very good.